This is a chemistry form 3 paper that I would like us to revise. This is the same paper that my students did for the end of term. We start with the first question. Describe the process by which nitrogen is obtained from air on a large scale. Now, the first step is usually removal of dust particles. So we start by saying pass the mixture through purifier to remove dust particles. Step number 2, we pass through concentrated sodium hydroxide or potassium hydroxide to remove carbon dioxide. Okay. So by now we have removed dust. So the first one is the removal of dust, followed by the removal of carbon dioxide. Then number 3, we cool to negative 25 degrees Celsius to remove water. When you cool to negative 25 degrees Celsius, the water changes to ice. The next step, we pass through a compressor. Now what happens in the compressor? There is repeated contraction and relaxation. Which converts air to liquid air at negative 200 degrees Celsius. Lastly, we carry out fractional distillation. When we carry out fractional distillation, nitrogen distills out first at negative 196 degrees Celsius. Followed by argon at negative 186 degrees Celsius. Finally, oxygen at negative 183 degrees Celsius. So you have got all the components. You have got 3 gases which you have obtained. Nitrogen distills out fast because it has a low boiling point of negative 196 degrees Celsius. followed by argon with negative 186 degrees Celsius, and finally oxygen at negative 183 degrees Celsius. Most students usually have a problem to realize which is lower temperature between negative 196 and negative 183. Most students think negative 183 is low while negative 196 is high, but in the actual sense, negative 196 is lower temperature than negative 183. For you to get it easier, you put it in a number line. When you put it in a number line, you realize that negative 196 is actually lower than negative 183. So I hope we have seen that the first step is passing the mixture through a purifier. After passing through a purifier, the next step, we remove dust. So we remove dust by passing through a purifier. After that, we pass through concentrated sodium hydroxide or concentrated potassium hydroxide. It must be concentrated. By so doing, we remove carbon dioxide. And then the next step, we pass through a compressor. When you pass through a compressor, in the compressor we have repeated contraction and relaxation. This one changes the air into liquid air. So the air changes from the normal gaseous air to liquid air, and that happens at a temperature of negative 200 degrees Celsius. Then after that, we carry out fractional distillation. When we carry out fractional distillation, nitrogen will distill out first, followed by argon, and finally oxygen. So apart from nitrogen, we get other components. This is a question of describe. Because it is described, it is a procedural question. There is a part we are supposed to start from, and there is a part we are supposed to end from. So if a student starts, let's say by saying, pass the air through concentrated sodium hydroxide, and he has not talked about removal of the dust, that student is already a non-starter and will not be able to get the answer. Let's move to the next question. That is question number 2. In an experiment to prepare nitrogen 1 oxide, ammonium nitrate was gently heated in a flask. Write the equation for the reaction that took place in the flask. Now in the flask, we have ammonium nitrate. This is the ammonium nitrate. It is a solid. We heat the ammonium nitrate. When we heat ammonium nitrate, we'll have water vapor, which is water in the gaseous state, and nitrogen 1 oxide. Nitrogen 1 oxide formula is N2O, and it is a gas. Then we balance. Nitrogen 1, 2 on the reactant side, nitrogen 2 on the product side. Hydrogen 4 on the reactant side, hydrogen 2 on the product's side. So we multiply by 2 to get it 4. When you multiply by 2, hydrogen becomes 4 and oxygen is now affected. Oxygen is now 2 plus 1, which is 3. And oxygen here is 3. So the equation is self-balanced. So when it comes to writing of chemical equations, the reactants and the products must be correct. The equation must be balanced. If the equation is not balanced, the student is penalized fully. So that student scores a 0. And if the student has not written the correct state symbols, or the state symbols are missing, then that student is penalized a half a mark. So if the student has got a correct equation which is well balanced but the state symbols are wrong or missing altogether, then that student will get a half a mark instead of 1 mark. But if it is balancing, the student scores a 0. Now the next question is, state and explain how the gas was collected. Now the gas was collected over warm water. Why over warm water? It is because the gas is soluble in cold water. Gas is soluble in cold water, but insoluble in warm water. In other words, the gas is collected over warm water because this gas is soluble in cold water, but it does not dissolve in warm water. Part C, a sample of the gas was tested with a damp blue and red litmus paper. When you see the word damp, it means moist. What observations were made? Now the observations that were made were as follows. We start with the word moist, blue, and moist, red, litmus papers does not change their color. Why do they not change their color? This is because nitrogen 1 oxide is a neutral gas. It is neither acidic nor alkaline. I hope you have seen the way you have written the observation. We begin with the word moist. So moist blue, moist red. Does not change their colors, and the reason is because of the gas is neutral, the neutral gas. So I want to emphasize on moist. Why emphasize on moist? The litmus paper does not change color if it is not moist. So we must say moist blue and moist red litmus papers does not change, because for the change to occur, the litmus paper must be damp or moist. We are now in question number 3. Iron 3 oxide was found to be contaminated with copper 2 sulfate. So you're having iron 3 oxide and copper 2 sulfate. Describe how pure sample of iron 3 oxide can be obtained. Now how can we go about this? So the first thing, we look at the properties of the solids that have been mixed. So 1, iron 3 oxide is insoluble, while copper 2 sulfate is soluble. So using this property, we need to understand the property of the components of the mixture, and we have known that iron 3 oxide is insoluble while copper 2 sulfate is soluble. Then the first step is actually to add water. This is another procedural question. You must follow the correct order in the procedure. So you say, we add water to the mixture in a beaker. When we add water to the mixture in the beaker, the next step is to stir to dissolve copper 2 sulfate. To dissolve copper 2 sulfate. Why to dissolve copper 2 sulfate? Because copper 2 sulfate is soluble while iron 3 oxide is insoluble. Okay, so you write to dissolve copper 2 sulfate, and then you say iron 3 oxide remains undissolved. So how do you separate the two mixtures now? We move to the next step, which is step 2. We filter. We filter to obtain copper 2 sulfate as filtrate and iron 3 oxide as residue. We were looking for iron 3 oxide. Therefore, we are going to deal with the residue. So you are going to say, that's now the last step, or step 3. Rinse the residue using distilled water. And dry in between filter papers. Now when it comes to drying, I encourage the students to dry in between filter papers, because in most cases we don't know whether the substance that is being dried contains water of crystallization or not, which can be lost by heating, or if it undergoes decomposition on heating or on warming. So the best option is to dry in between filter papers. And to get a pure sample, we must do what? We must rinse. So rinsing is to make sure that all impurities, like for example, all the copper 2 sulfate that were in contact with our iron 3 oxide are removed. So we rinse. To remove what? To remove any copper 2 sulfate that was remaining. And then it is now pure. Once it is pure, we need it dry. How do we dry it? We dry it by placing in between filter papers. We move to the next question. Study the diagram below, then use it to answer the questions that follow. Now the question that is being asked here is to draw the wooden splint after it has been removed from the setup that we have. So the first thing that we draw is to put the wooden splint, to show the wooden splint. This is our wooden splint. Then this part here is going through the pale blue. It has been placed on the pale blue region, which is less hot, which is very hot, sorry. So if I were you, I'll place a mark here. It will become dark. You place a mark here, it will also become dark. Then the middle will not become dark. Then you transfer what you have seen here down here. So you place it like this, and then like this. Then you shade this one to become dark, and this one to become dark. That's the way you did here, because this part is pale blue and it is very hot. So you label, you can say this is the burnt part, or charred parts. Okay, burnt part or charred parts. Then this one is unburnt or uncharred parts or part. The next part of the question will be explain the observation that is made. Now we are going to explain why this part was unburnt and why this part was burnt. So we are going to explain by starting with the unburnt or uncharred part. So we'll say uncharred part, okay, uncharged part was placed in the middle here is the almost colorless region. In the less hot, almost colorless region that contains unburnt gases. Okay, so uncharged part, not uncharged, uncharged part was placed in less hot. Why is it less hot? Because it is the almost colorless region that contains unburnt gases. So it is less hot because the flame is less hot because it contains unburnt gases. Okay, now we have got this other part, which is the burnt part or charred part. So why is it burnt or charred? So burnt parts. Why are they burnt? It is because they were placed in the hot pale blue region that contains completely burnt gases. So the student will wonder, why is this part very hot? So it is very hot because it contains completely burnt gases. I hope you are very keen to realize that this part is the outer region. So this outer region is actually supplied with a lot of oxygen from the nearby areas. Okay, as the flame is burning, oxygen is coming in from the neighboring regions like this, and therefore the outer region burns completely because there is sufficient supply of oxygen. We move to question number 5. We are done with this part. We have answered already. State the Boyle's law. Now the Boyle's law gives the relationship between the volume of a fixed mass of a gas and its pressure. So usually this one says volume of a given mass of a gas is inversely proportional to its pressure comma, temperature kept constant. So you can be asked, state the assumption of Boyle's law. You'll say temperature is kept constant. That is the assumption. Okay, you can also be told to give the mathematical expression. So the mathematical expression can be this one. Volume, that's the proportionality sign. Inversely proportional, that is 1 over P. Remember, temperature is kept constant, so you put temperature in brackets like that. Or you can give this one. Volume is equals to constant divided by pressure. Or you can give this one. Pressure 1, volume 1 is equals to pressure 2, volume 2. So these are the mathematical expressions, while on top here, this is the assumption of the law. We move to the next question. Part B, 5B. A gas occupies 500 cubic centimeters. So this 500 cubic centimeters is volume 1 at that 7 degrees Celsius. So that 7 degrees Celsius is temperature 1. So this temperature 1 is supposed to be 273 plus 37, which is going to give us 310 Kelvin. So that is temperature 1. Then you have this value here, 100,000 pascals. This is pressure 1. So you already have a volume 1, we have temperature 1, and we have pressure 1. What will be its volume? Now this is the question. Volume 2 is what we have been asked. What will be its volume? So volume 2 is what we don't know. At 10 degrees Celsius, 10 degrees Celsius is now temperature 2. So temperature 2 will be 273. We add 10, we get 283 Kelvin. That is temperature 2. And then, 101,325 pascals. This is now pressure 2. I hope you have noted that temperature in our calculation must be in Kelvin scale. You don't operate with temperature in degrees Celsius, you must convert it into Kelvin scale. So we are going to make volume 2 the subject of the formula using the combined gas law. So the combined gas law is like this. Pressure 2, volume 2, divided by temperature 2 is equals to pressure 1, volume 1, divided by temperature 1. You can start with pressure 1, volume 1, divided by temperature 1, and with pressure 2, volume 2, divided by temperature 2. But for my case, I've begun with pressure 2, volume 2, divided by temperature 2 because I want to make volume 2 the subject of the formula. So here we multiply by temperature 2 and divide by pressure 2. Here we multiply by temperature 2. What we do here, on the reactant side, we do it on the product side. Divide by pressure 2. So pressure 2 will cancel pressure 2. Temperature 2 will cancel temperature 2. So volume 2 is equals to pressure 1. Now pressure 1 is the value that we have here, 100,000 pascals. So right here, 100,000 times volume 1. Volume 1 is 500 cubic centimeters. So we multiply by 500 cubic centimeters. And then we multiply by temperature 2. And temperature 2 is 283 Kelvin, what we have here. Then you divide by temperature 1, and temperature 1 is 310 Kelvin. We multiply by pressure 2, and pressure 2 is 101,325 pascals. You work out all this. The answer is 450.48 cubic centimeters. And that is our answer. We move to question number 6. Describe how a solid sample of copper 2 carbonate can be prepared starting with copper metal. Again, this is another procedural question. We cannot react copper directly with carbonic acid to form copper 2 carbonate. Why? Because copper is below hydrogen in the reactivity series. So we are going to start first of all by oxidation of copper. We are going to start with this copper. We oxidize this copper to form copper 2 oxide. So we are going to start with the first one. We say heat copper strongly in air to form in air to form copper 2 oxide. To form copper 2 oxide. Sorry. Yes, to form copper 2 oxide. We are right. Step number 2. We have copper 2 oxide. What do we do to the copper 2 oxide? We react with an acid that will give us a soluble salt of copper. So you can say react excess copper 2 oxide with dilute nitric 5 acid. Okay, here we form copper 2 nitrate. Okay, so we say to form copper 2 nitrate solution. To form copper 2 nitrate solution. Why did I choose nitric 5 acid? It's because from our knowledge of form 2 work, all nitrates are soluble except none. So we are very definite that if we react nitric 5 acid with copper 2 oxide, will form a soluble salt. So we need this soluble salt for the next step. Okay, so next step, we had reacted excess copper 2 oxide with dilute nitric 5 acid. We need to remove this excess copper 2 oxide. So we say filter to remove excess copper 2 oxide. We have removed the excess copper 2 oxide. Now we are remaining with copper 2 nitrate, which is a filtrate. Okay, so you can say here and obtain and to obtain copper 2 and to obtain copper 2 nitrate as filtrate. Okay, we have obtained the filtrate. What do you do to the next step? That is step number 4. So we are going to take a solution of sodium carbonate or potassium carbonate and add to copper 2 nitrate. We use a soluble carbonate, and you have got only 2 soluble carbonates in the lab: sodium carbonate and potassium carbonate. Ammonium carbonate is also soluble, but it does not exist in solid state. So you say add a sodium carbonate solution to the filtrate to precipitate out copper 2 carbonate. Okay, I hope we still remember that all carbonates are insoluble except sodium carbonate, potassium carbonate, and ammonium carbonate. Okay, so we have precipitated out copper 2 carbonate. So what's the next step? Filtration again. Okay, so we now say filter. We want copper 2 carbonate, so we filter. Okay, filter and then rinse with what? With distilled water. Rinse with distilled water. Okay, filter and rinse. What are we rinsing? Residue. With what? Distilled water. And then what do you do finally? And dry in between filter papers. There are a few things that I would like us to note about this question. 1, this question is a procedural question. Okay, therefore, if you don't start with heating the copper copper metal strongly so as to form the copper 2 oxide. That is the end of it. This question again tests your knowledge of the reactivity series. You must be aware that copper is below hydrogen in the reactivity series. So you cannot react copper directly with the acid like carbonic acid says to form copper 2 carbonate. Maybe you can react copper directly with something like nitric 5 acid, dilute or concentrated. That is still okay. But the problem with that formula, it produces a lot of fumes of nitrogen 4 oxide, which are very poisonous. Now, we are now in question number 4. Give the name of the third member of the alkene series. So I want us to note the following, that the first member of the alkene series is ethene. Okay, so first member has 2 carbon atoms. Okay, so member, we can have here member. Okay, then here you have number of carbon atoms. Okay, and then here we have member number, so that you can have it cleanly. Now the first member, the number of carbon atoms, 2. The first member having how many carbon atoms? 2. What is the name? So here is member name. The name is ethene. Why is the first member ethene? Because for a carbon-carbon double bond to be formed, we must have at least 2 carbon atoms. So the first member is ethene. So member number 2 will be having 3 carbon atoms. Therefore, this member will be propene. So this is member number 2. Then we go to the third member, will be having 4 carbon atoms. Okay, and the name will be butene. So the answer is here. The fourth member will be having how many carbon atoms? 5. And the name will be what? Pentene. I hope you have noted. Our response is this one. I just wanted to show you the member number versus the number of carbon atoms and the name. Member number 1, 2 carbon atoms, name ethene. Member number 2, 3 carbon atoms, name propene. Member number 3, 4 carbon atoms, name butene. And I hope you have realized that we do not have an alkene with 1 carbon atom, so there's nothing like methene. Okay, now let's go to the next question. Draw and name all isomers of butane. Now, in butane, we have got only 2 isomers. The first isomer is this one. 1, 2, 3, 4. Okay, those are 4 carbon atoms. Then you place hydrogen like this. These are hydrogen atoms like this. Now this is normal butane. Okay, we move to the second one. We have 1, 2, 3. Okay, like this. We put the branch. This already has how many carbon atoms? Butane has got 1, 2, 3, 4 carbon atoms. Here, in our second member, we have got 1, 2, 3 carbon atoms in the longest continuous chain. So, we cannot place a branch in the first carbon atom nor the last carbon atom. So, the branch should be in between. So, our branch will be here. And we place hydrogen in those which are hanging like this. Like that. Now what will be the name? This is carbon number 1, carbon number 2, and carbon number 3. So the parent name is propane. Why propane? Because the longest continuous chain has got 4 carbon atoms. But in carbon number 2, we have a branch, and that branch is a methyl branch. So the name will be as follows: 2 for the position of the branch, followed by hyphen, then methyl, which is the name of this branch here. So 2 for the position of the branch, methyl, the name of the branch, and then we conclude by writing the parent name, which is 2-methyl propane. That was question number 7B. So these are isomers because they have the same molecular formula. What's the molecular formula? The number of carbon atoms, C, and then the number of hydrogen atoms, we see for the 2, carbon and hydrogen. How many carbons are here? 1, 2, 3, 4. So here is 4. What about here? 1, 2, 3, 4. So carbons are 4. So the number of carbon atoms are the same. What about hydrogen? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So here, hydrogen 10. What about here? Hydrogen 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So here, you are getting to know the meaning of an isomer. Isomers are compounds which have the same molecular formula, like these isomers of butane. Molecular formulas are the same, C4H10, C4H10, but have different structural formula. The structure of normal butane is not the same as the structure of 2-methyl propane. So the structures are different. That is why the names are also different. We move to question number 8. Draw a diagram to illustrate electrolysis of molten aluminium oxide. So when we are drawing this, we start with a long stroke followed by a short stroke, and then another long stroke and another short stroke. A long stroke and a short stroke represents a dry cell. One long stroke, one short stroke is one dry cell. So if we have got 2 long strokes and 2 short strokes, then this one is a battery. 2 dry cells which have been put together. So what do? You put like that, and you move down like this. You move down, you connect it to an electrode like that. You connect this one to another electrode like this. After that, you show a crucible like that. After showing a crucible, show that your molten substance is inside there. Show a tripod stand. Show a means of heat. Show that this is the molten substance like that. And then not forget to show the wire gauze like that. So labeling, this is a battery. Okay, this is a connecting wire. Connecting wire. This is carbon. This is also carbon. It's something I would like us to talk about, this carbon. The long stroke is the positive terminal of the battery. The short stroke is the negative terminal of the battery. Okay, now the electrode which is connected to the positive terminal of the battery is the positive electrode, and it is known as anode. So this is carbon anode, and therefore it is positive. And this is the carbon, and this electrode is connected to the negative terminal of the battery. So this is carbon cathode. Carbon cathode, and it is the negative electrode like that. This is a crucible. Label as much as you can. This is a wire gauze. You write wire gauze. A tripod stand. Tripod stand. And finally heat. I've forgotten one thing. Now inside here we have molten aluminum oxide. Molten aluminum oxide, which means it is in liquid state because of the heat. So this is molten. You can even place liquid like that, indicating that it is molten. We move to question number 9. A molecule of a compound has a mass of 7.34 times 10 raised to negative 23 grams. Calculate its relative molecular mass. So here you have been told that one molecule has a mass of 7.34 grams times 10 raised to negative 23. So, and we want to know the molar mass. And this is the number of molecules which are present in 1 mole of a substance. So it say if one molecule has a mass of, you put an arrow to show that it contains this, has a mass of 7.34 times 10 raised to negative 23 grams. Therefore, what about the number of molecules which are present in 1 mole of that compound, which is this number of molecules? So it say therefore 6.023 times 10 raised to the power of 23 molecules will be what mass? So it will be what? We do cross multiplication. The number of molecules in a mole, which is 6.023 times 10 raised to the power of 23 times now 7.34 times 10 raised to negative 23, and then we divide by 1 molecule. Now 10 raised to 23 times 10 raised to negative 23. When we add the indices, this will become 10 raised to 0, which will become 1. So we multiply 6.023 times 7.34. In other words, this one cancels this one. And the answer that we get is 44.209. The answer is 44.209. You leave the answer like that. Reason is because this is relative molecular mass. Anything that starts with the word relative is a ratio, and ratios do not have units. State the Avogadro's law. Now Avogadro's law states that equal volumes of gases, contains equal number of molecules. And that equal number of molecules is 6.023 times 10 raised to the power of 23 molecules. That is if the volume is that of a mole. Okay, you put a comma and then you conclude by saying temperature and pressure. Temperature and pressure kept constant. Temperature and pressure kept constant. Question number 10. Name gas X. Now gas X is oxygen. Okay. Write an equation for the reaction that produces gas X. Now here we have chlorine water, which is a mixture of hydrochloric acid and chloric 1 acid. Now the gas X is produced by chloric 1 acid. So inside here we have chloric 1 acid and hydrochloric acid. Now this chloric 1 acid is unstable and it is the one that produces oxygen. So we write the equation like this: HOCl. This is a solution. Okay. We decompose in the presence of UV light. UV light is the same as this sunlight that you are seeing here. So sunlight decomposes chloric 1 acid to form hydrochloric acid and oxygen gas. Now we balance the equation: hydrogen 1, hydrogen 1, oxygen 1, oxygen 2. So we multiply by 2 here. Then it will affect hydrogen and chlorine. 2 hydrogen, 2 chlorine. 1 hydrogen, 1 chlorine. We write here 2 and the equation is balanced. So again, I'll remind you that if the equation is not balanced, you get a 0. If the equation is balanced but the state symbols are wrong, then you lose a half a mark. So if it is a question of 1 mark like this one, by not writing the correct state symbols, you just score a half. So what are the uses of chlorine? So 1, treatment of water. Treatment of, it can be water. It can also be sewage. Treatment of sewage, treatment of water. Then you can have manufacture of the following. You can have manufacture of hydrochloric acid. Okay. Manufacture of bleaching agents. Manufacture of bleaching agents, e.g. sodium hypochlorite, which is NaOCl. Get these ones include things like Topex, Vim, Jig. Those are bleaching agents. What is the meaning of polymerization? That's question number 11. Now, polymerization refers to formation or the process of forming a long chain alkane. Sorry, a long chain molecule, not alkane, a long chain molecule. Okay. That long chain molecule is also known as a polymer. Okay. Polymer. From joining. Many short chain molecules. Okay, so the short chain molecules are known as monomers. We move to question number 12. It is number 11b. Draw and end the structure of the polymer formed from propene. Now the structure of propene is C, double bond C, and then CH3, like this. This is propene. Okay, so here you have hydrogen, and you have hydrogen. Now, what we do, we take carbon, okay, and then carbon. We are dealing with this part here. This hydrogen, you bring it down here. That is this hydrogen, is this one. Okay, this hydrogen, you bring it down here. Okay, and then up here we take this other hydrogen. So this hydrogen is this one is this one. Okay, We are remaining with this C3 group. So this C3 group, we take it up here. Okay. Then you put an extension and another extension here. Then you put a bracket like this and another bracket like this. Then you put N. And this is now known as polypropene. Polypropene. Okay. Question number 12. A sample of 0.63 grams of lead powder were dissolved in excess nitric 5 acid to form lead 2 nitrate solution. All the lead 2 nitrate was then reacted with sodium sulfate solution. Write an ionic equation for the reaction between sodium sulfate solution and lead 2 nitrate solution. Good. So the ionic equation, lead ions in lead 2 nitrate, okay, combines with sulfate ions. Okay, the sulfate ions are from sodium sulfate to give us lead 2 sulfate solid, a precipitate. Okay, we have said lead 2 ions are coming from who? From lead 2 nitrate. Okay, lead 2 sulfate is from lead 2 nitrate, while sulfate ions are from sodium sulfate. So lead 2 nitrate donates lead ions. Sodium sulfate donates sulfate ions. When they combine, they form a precipitate of lead 2 sulfate, which is an insoluble salt, and it is balanced. Determine the mass of lead salt formed in the reaction in A above. First, we show the reacting mole ratio, lead ions to lead sulfate. Okay. Now lead ions, the mole ratio is 1. Lead sulfate, the mole ratio is 1. So the mole ratio is 1 to 1. So what does this tell us? 1 mole of lead ions produces 1 mole of lead sulfate. And what is the mass of 1 mole of lead? So you'll come here and say, if 1 mole of lead, which is 207, gives us 1 mole of lead sulfate, and 1 mole of lead sulfate is 303 grams. Okay, so 1 mole of lead, which is 207 grams, gives us 1 mole of lead sulfate, which is 303 grams. What about 0.63 grams of lead powder? So you'll say, well, therefore 0.63 grams will give us how many grams? We do cross multiplication and we get the answer. So it will be 0.63 times 303, and then we divide by 207. So when we work out that, we get 0.9222 grams. Okay, and you give your answers in most of the calculations in chemistry. Make sure that you give them to 4 decimal places, whether they are moles or any other calculation. Try to give it to 4 decimal places. Number 13. For each of the following experiments, give the observations and the type of change that occurs. A few drops of water are added to small amount of anhydrous copper 2 sulfate. So anhydrous copper 2 sulfate is white. So you'll say the color changes from white to blue. To indicate that color changes from white to blue. What type of change is this? This is a temporary chemical change. It can easily be reversed. Even though it is a chemical change, it is a temporary chemical change. Temporary chemical change. Okay. We come to the next. A few crystals of iodine are heated gently in a test tube. So the crystals of iodine are black. When they are heated, they change to a purple vapor. So you say black crystals changes to purple vapor. Okay, what type of change is that? That is a temporary physical change. Temporary physical change. We move to question number 14. What is the role of the following parts during the fractional distillation of a mixture of water and ethanol? Fractionating column. Now the fractionating column has got two main roles. The first role is that it allows the fraction or fractions to condense into liquid, and fall back to the flask before its boiling point is reached. Before its boiling point is reached. Okay, that is one. Now the second role of the fractionating column is that it acts as room for holding glass beads. This is where the glass beads are held, or it holds the glass beads. What is the role of the glass beads in the fractionating column? This one increases surface area for condensation. We move to question number 15. Any one application of fractional distillation process. Okay, so we now mention where fractional distillation works. We can talk about the following: fractional distillation of one, crude oil. Another one is fractional distillation of liquefied air, like for the case of obtaining oxygen, argon, and nitrogen. Number 15. Carbon dioxide does not support combustion, but burning magnesium continues to burn in carbon dioxide. Now the heat from the burning magnesium decomposes carbon dioxide to carbon and oxygen. Then oxygen continues to support burning. Okay, you see heat from burning magnesium decomposes carbon for oxide to carbon and oxygen, which supports burning. Write an equation for the reaction in A above. So we need to write an equation for the reaction between magnesium, our solid, and carbon dioxide, a gas. So magnesium will combine with oxygen to give us magnesium oxide, a solid, and carbon will be left alone. Now we balance the equation. Magnesium 1, carbon 1, oxygen 2, oxygen 1. So you write 2 here. When you write 2, it will also affect oxygen, magnesium. So you write also 2 in magnesium. Question number 16. The diagram below is a section of a model of the structure of element T. In the middle we have charged nucleus, and outside you have an electron. State the type of bonding that exists in T. So the bond here is metallic bond, okay, or metallic lattice. B, in which group of the periodic table does element T belong? Give a reason. Now you'll check at each charged nucleus, you see the number of electrons which are surrounding each charged nucleus. So for this charged nucleus you have this one, for this one you have this, you have this one, you have this, and this one you have this. So we have one electron which is surrounding the charged nucleus by atom. So it means this one is a member of group 1 because they have one delocalized electron by atom. So we write here group 1. Explanation, you say, has one delocalized electron, okay, per atom in the lattice. Good. We move to question number 17. Below are pH values of some solutions. Which solution is likely to be acidic rain? Now acidic rain is weakly acidic. So the one which is weakly acidic is Z. 6.5 shows that the solution is weakly acidic. Potassium hydroxide. Potassium hydroxide is strongly basic. Therefore, the correct response is Y. Okay. Substance V reacted with both solutions Y and X. What is the nature of V? So solution V is strongly alkaline, while solution X is strongly acidic. A substance which reacts with both strong acid and strong base is said to be amphoteric. So the nature is amphoteric. We move to the next question. We can start with question number 19. We clear with question, or we can just start with question number 18. Draw a setup that can be used to prepare dry hydrogen gas in the laboratory. So first, we show a dropping funnel. This is the dropping funnel, like this. Being a dropping funnel, it should have a top. We show the top like that. Then we show a conical flask, but before we show the conical flask, we should show how the gases are getting out. So this is our conical flask. So this is where the gas is generated. So here we have drops of the acid, and here we have granules of zinc. So here we show the stopper. Now, I hope you have seen that I have not blocked where the acid will come in through, and I have not blocked where the gas is moving out from. So here we have zinc granules. Okay, this is a tap. Up here we have dilute HCl. So we are reacting dilute hydrochloric acid with zinc to produce our hydrogen gas. Okay, this is a cork stopper. Cork stopper. This is a conical flask. Conical flask. Okay. From here, our gas enters another conical flask. And here, it dips almost to the bottom. Okay, why are we dipping almost to the bottom? Then we have our solution. The solution is concentrated sodium hydroxide or potassium hydroxide. What is the function? This one absorbs fumes of hydrogen chloride or hydrochloric acid, which reaches the other side. Good. So we must show again the gases which have escaped. So we look at this one, we draw this one very keenly, taking care not to block the delivery tubes, like that. So once we are done like that, we now dry our gas and collect it. We dry using concentrated sulfuric 6 acid. Okay. Okay. So again, this one dips to the bottom, like that. We leave a small space, and then we collect our gas. Okay. Okay, let me just clear this drawing first. Let me explain a few things here and there. So this one is concentrated sulfuric 6 acid. Okay, this is now used to dry the gas because we required dry hydrogen gas. Okay. Now, for a good number of students, usually do not know which gas is less dense and it is collected by which method. So for them, I advise that you draw that you are collecting this through using a syringe like this. Use a syringe to collect, because a syringe collects all gases. Just like this. And you are done. Just show that there's some connection here. Just like that. So this is the syringe for collection of the gas, and this is the delivery tube. Now, label as much as you can, because labeling, or a question that requires you to draw, is actually meant to test your knowledge of apparatus. So label as much as you can. Number 19, the grid below represents a part of the periodic table. Study it and answer the questions that follow. Letters are not the actual symbols of the elements. How does the atomic radius of K compare to that of L? Explain. So the atomic radius of K, okay, is larger than that of L, or the atomic radius of L is smaller than that of K. Okay, so you can say L is smaller than K. Why is it smaller than K? It's because of increase in number of protons across the period. Due to increase in number of protons across the period. Some students will say due to increase in nuclear charge across the period, or due to increase in nuclear force of attraction across the period. That is still correct. Element R forms an oxide of the formula RO2. So this is our oxide, RO2. Okay, and we know that the valency of oxygen is 2. We don't know the valency of R. So if this is 2, and this is also 2, then it means this is 4. It's multiplied by 2. So this is 4. So we write this one is 4. And then this one is 2. So write this one is 2. You switch. So when you switch, this 2 comes here and the 4 goes there. When you simplify, it will give us this. So it means R is a member of group 4 of the periodic table. So it comes to group 4 and then just above L. Okay? Sorry, just above L. Indicate the position of the grid. So we go to period 2. Period 2, group 4. So you write R at the top there. Lastly, write down the formula for the compound formed between K and P. So here we have element K and we have element P. Element P is in group 7, so it reacts by gaining 1 electron. It forms a charge of -1, or its valency is 1. Then element L is in group 1, 2, 3. So it is in group 3. Therefore it reacts by gaining 3 electrons. Sorry, by losing 3 electrons. So therefore we'll have a charge of 3 positive. So to get the formula, you switch the charges. So here we have Kp. K will take the charge of P, so it will be K1. And P will take the charge of K, therefore it will be 3. So the right answer is Kp3, or K1P3. Thank you. Subscribe to our YouTube channel. Follow us in TikTok if you like our work for more interesting lessons and more interesting learning.